So, hi everyone. It's a pleasure to be here. Essentially, I'm going to give you a crash course. It's going to be very crash course. I have a lot of things to do, to talk about. I'm going to speak quite fast to make sure that I end things on time. Essentially, like Gilles mentioned, we have been working in this kind of crazy software called Sound Particles that it uses computer graphics techniques applied to sound, and essentially it's being used by major Hollywood studios for those epic movies with sound battlefields and all of those things. So essentially, all of the things that I'm going to talk today about 3D audio, it were things that we had to handle with our software. So the idea is to, okay, let's give you a very quick overview about all the different flavors of 3D audio that we have, and how can you, as a developer, start working with them. So essentially, I'm going to focus on these four main flavors of 3D audio. I'm going to talk about channel-based audio, object-based audio, Ambisonics, sometimes also known as scene-based audio, and binaural. I'm not going to give you code. I'm going to essentially to make sure that people tend to better understand this format, to make sure that people start doing great, continue doing great work regarding plugins for 3D audio. So let's start with channel-based audio. So we're going to start with stereo. So we have two speakers, and the idea is, yes, if you have two speakers and if you place the same audio in both speakers, what happens is that you get this phantom image, and your brain is going to think that the sound comes from the front. And if you start changing the gains in each one of those speakers, this phantom image starts to go from left to right and right to left. Also, when I talk about stereo, we usually are talking about an angle of 60 degrees. And why 60 degrees? Well, you want the maximum angle possible because you want a wider sound image. But what happens is that if you have this angle and this angle becomes too large, what happens is that the virtual image is going to collide. And instead of having a sound that it feels like coming from the front, actually your brain is going to start thinking that you have two sounds coming to the sides and nothing coming from the front. So essentially you want a larger angle, but not too large, because otherwise stereo stops working. So essentially that's why people tend to use an angle of around 60 degrees to get the maximum widest possible frontal image. Then there is the addition of a central speaker. Okay, so you have a new speaker between the left and the right, and the question is why? Because if you have a stereo, you have already a frontal image. Why anyone could eventually want this additional center speaker? And actually, I've been talking with even top professionals mixing mixing music for top artists, and sometimes they say, okay, I don't even use the central channel, so why the hell do we need this central channel? Well, essentially, that's because the world is not a perfect place, which means in 3D audio that not everyone stays on the sweet spot. Okay, so if you are going to see a movie, okay, yes, there are a few that are going to be positioned on the sweet spot, but a few of them are going to be positioned close to the screen, which means that their angle between left and right is going to be much more than 60 degrees. So they're going to have a hole on the middle. Or if you are on the side of the sweet spot, you're essentially going to get much more weight from the speaker that is near you. So by adding this central speaker, essentially what you do is you are adding an anchor that gives you less distortion in terms of image. Not about distortion, but the distortion of the sound image. Also, at some point, people decide, okay, let's start to explore other zones besides the frontal image. And to do that, people start with left, center, right, surround. That essentially it was one audio file, one audio channel that was fed into two speakers. And then with 5.1, you get independent speakers, left surround, right surround. And if you go to movies, what happened in movies is that instead of having one speaker for each channel, you actually have an array of speakers. So you go to the movie theater and you see an array of speakers on the left wall, another array on the other wall, and essentially it's an array of speakers, but all of them are playing exactly the same. Why? Because essentially, once again, you don't want olds, people are not on the sweet spot, and by making sure that you have this wall of speakers, make sure that there isn't any olds in terms of the image. Then we have subwoofer, and mainly in movies they decide, okay, we need more impacts on low frequency, especially the earthquakes, the explosions, all of those things. And as you know, we are not very, we don't have a lot of sensibility in terms of low frequencies, which means that you need high SPL levels to actually start listening to something there. So you would need a lot of power to get these low frequencies. So there was two possible approaches. One of them was, okay, let's simply get bigger speakers, more powerful amplifiers. Well, what was the problem? Not only this was an expensive solution, but remember that at this time you had limited dynamic range, which means that essentially if you need this huge dynamic range for the low frequencies, it means that everything else must be over here, and then dialogue will be over here. And if you have problems with dynamic range, you're going to have a lot of noise with dialogue and so on. So the decision was, okay, let's have one single low frequency channel with one subwoofer reproducing everything, and that's the reason why you have one additional channel and not having simply bigger speakers, more powerful amplifiers. Also quite important, be careful, because when you're talking about LFE and subwoofer, they are two different concepts. So LFE, it's the channel that brings this low frequency content, and then the subwoofer, it's the speaker that reproduces the low frequency content. Also, there are several other layouts in terms of surround sound. At some point there was the 6.1, also there was the 7.1 from Sony SDDS with 5 channels on the front and 2 surrounds, but then we have the traditional 7.1 that we use nowadays with 3 speakers on the front and 4 channels on the surrounds. So now imagine that you want to create something for, create a simple thing like a panner. Okay, how can I do that? You're probably, first idea would be to create something like this. So you have a left and a right, and you simply do a linear curve between all of them. And this is probably not the best approach, unless you are too worried about mono-compatibility, because essentially what you want is you want to make sure that the power coming from the speakers continue exactly the same as you pan sound around. So essentially, to make sure that the power stays the same, what you need to do is the left gain, the square of the left gain and the square of the right together, it's 1. So essentially you get a different kind of curve. So in the middle, if you want something coming from the front, what you have to do is not to give you a gain of 0.5 to both speakers. What you do is a gain of 0.707 to make sure that the sum of the squares continues to be 1. Also, sometimes in terms of software, these different curves appear as a -6 dB panning law or -3 dB panning law. So essentially you are talking about which is the level of the central point. And for this common power, essentially there are several formulas. If you want to simply create a single panning pot, you simply use this sine law. If you want something more accurate, you use this tangent law. Now imagine that you want to pan something for surround. So what you do in surround, it's exactly the same thing. You choose the two in-between speakers, and then you apply the same things. And be careful, because the two in-between speakers are not the speakers that are close together. Because, for instance, if I have a sound over here, the two close speakers are those two, where essentially you want between these two. Okay, so be careful, it's not the closed one in terms of algorithm, it's the in-between. And then you simply apply the same thing, but only considering those two channels. Now let's talk about immersive audio. And when you talk about immersive audio, essentially what you are talking about is surround with height. So it's some kind of system that, besides handling the surround sound, it also works with some kind of height component. Okay, so usually means that you have some speakers not only at the horizontal plane, but also above you. And then you have new formats like Auro, IMAX, NHK, and others. So for instance, in this case, what we have here on the images is we have this layer. This is Auro 13.1. So you have a 7.1 layer horizontal, and then 5.1, 5.0 layer, usually with elevation of 30 degrees. And then finally, you have a channel, a speaker coming from above you, usually called the voice of God for obvious reasons. So you get these 3 layers to explore sound coming from all the directions. And if you want to actually implement this kind of solutions, what you do is use vector-based amplitude panning. So what is VBAP, vector-based amplitude panning? Well, essentially it's the same thing like we do in stereo, but now with 3 speakers. So we have this triangle, okay, and by controlling these 3 gains, you can create this virtual image that, depending on the gains, is going to move around that triangle. So essentially, the same concept, 3 gains, and what you do is, considering that this vector P represents the desired location that you want the sound to come from, what you do is you use these 3 gains, considering the vectors of the positions of the speakers, and by doing this, you get the sound coming from that target position. And also make sure that the sums of the squares continue to be equal to 1 to make sure that the power is always the same. So if you want to apply VBAP, one of the things that you need to do first is you need to create this set of triangles. So imagine that you have a speaker configuration like 13.1 or 12.0 from IMAX or any other. So essentially what you need is, first of all, okay, let's do the triangulations. Let's create these triangles. And if you are using a fixed setup like Auro or something like that, you can even hard code this and you say, okay, my triangles are the center, left, top, center, blah, 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 and you create everything hard coded. If you want the users to be able to enter some custom configuration, then what you need to do is something in mathematics called a convex hull that essentially creates all the triangles to make sure that, for instance, there aren't triangles overlapping, or eventually that there are areas, 3D areas that are not covered by any triangle. So there is something that you need to take into consideration. Also, and then what you do is, based on the desired sound position, you say, okay, I want the sound coming from there. So what you do is you find out the right triangle that intercepts that direction, and then you obtain the gains for those 3 speakers of that triangle, and you apply all of this. Sometimes it could also help you create the concept of virtual speaker. What is this? So imagine that you are creating a video game. You want people to have like a 5.1 system, okay? So you want a sound from a helicopter or something that is come from height information, but you only have a horizontal plane, okay? So if you want a plane and the plane comes from here, okay, and if you use only azimuth, what happens is that this is going to say, okay, it's from front, okay? That could not be the best solution, because it's front, and then suddenly it starts to go for the surround. So sometimes what we do is we create this concept of virtual top speaker that actually is not there, or a bottom speaker that actually is not there. You still do all the VBAP, vector-based amplitude panning, considering that's a speaker there. And then what you do is the signal that actually should come through this speaker actually is sent to every single speaker. So as the sound starts to go to a height position, essentially it's going to be sent to every single speaker instead of using only azimuth. Also, sometimes imagine that you have a sound and you have the sound that is moving like this, passing by car, and okay, no problem, you still apply all the traditional panning. What happens now is, imagine that you have a sound that comes in front of you and passes through the listener. Okay, what happens, once again, is you want the sound coming here and say, okay, center, 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 and from a moment to the other, it's going to be in the rear, okay? And to prevent this kind of abrupt situations, what you need to do is you can either do some kind of crossfade based on time, okay? Or eventually you can use something like the concept of a minimum distance. And this concept of minimum distance essentially tells us that if the sound starts to come too close to the listener, at some point that sound becomes like an omni kind of sound. So essentially that sound, it's going to be spread to every single speaker. So essentially its center starts to be in every single speaker and then back to the rear speakers. Okay, so this is something that you could also need to take into consideration. So channel-based audio. The good news is that, okay, this is perfect if you already know the output layout that you have. So imagine that you want to create something in 3D sound. If you already know that this is going to be the final layout, great. Use channel-based and channel-based audio. What are the problems? Well, the problems is that if you change layout, you're going to need a new mix. Okay? If you are doing movie and you want a mix in 5.1 and 7.1, actually you need to mix the movies twice, okay, to make sure that you have a mix for 5.1 and another mix for 7.1. So the question is, could we eventually have some kind of format that would be completely independent in the terms of the output channel format, something that it doesn't matter how many speakers or where they are located, that still would be able to work? Okay, so that's the concept of object-based audio and also the concept of Ambisonics. So let's start with object-based audio. With the channel-based audio, what we have seen now, what we do is, yes, we have our sound, and now it's most of the times in mono. Then we're going to have a panner that will going to distribute the sound to the several channels, okay? We get all of those channels, we're going to distribute all of those channels, like 5.1, and then in the during reproduction, each one of those channels is going to be reproduced by a single speaker, okay? With object-based audio, what you do is you don't mix sounds. So you have the sound, okay? We are not going to mix the sounds. You are going to send all the sounds independently to through distribution into the final reproduction place. Yes, we have the panner, but the panner only gives you 3D information and say, okay, this sound should come from there, and this sound should come from there and move like this. So you get this parametric information, this metadata. You distribute also this metadata, and then during reproduction, and based on the speaker layout that you have on the reproduction, then it's where you're actually going to do the final render of everything. If you say, the sound should come from here, and if on my room I actually have a speaker there, then I'm going to use that speaker to reproduce the sound. If I have another speaker there and another there, then I'm going to use both of them to reproduce the sound. So essentially, it's a system that works with every single layout. So we are not mixing sounds, okay? Let's keep each channel independently. Let's add some additional metadata like the 3D position, the size, the movement, all of those things. Let's distribute all of those streams, and then during reproduction, based on the layout of the speakers, based on the metadata of each sound source, the render engine is going to decide where to place, what should be placed in each speaker, like that. So, object-based audio. An example for people to understand a little more. So, Dolby Atmos, it's the most known one. Essentially, has support for 118 audio objects plus a 9.1 bed, which means that if you have a movie in Dolby Atmos, essentially you can send up to 128 audio streams back to the movie theater, okay? Independently, and then on the movie theater you are going to render those channels for the speakers. Also, Dolby Atmos supports up to 64 independent speakers, so essentially you can have a movie theater with up to 64 independent speakers, which means that each speaker will be completely independent from all the other speakers. This is the image of a panner, and what it changed with Dolby Atmos regarding a regular 5.1 or 7.1 room. Essentially, with a regular 5.1 and 7.1, the surround speakers starts more or less 1/3 of the room. With Dolby Atmos, they go up to the screen. Also, you have 2 rows of speakers above you, okay, to explore the height. And besides, like I mentioned, each one of those speakers is completely independent from all the other speakers, so it gets you the most of this 3D audio. Besides objects, most of those formats also support some kind of channel-based audio. Usually, with Dolby Atmos, you have a 9.1 bed, so it's almost like a 7.1 with additional 2 channels on the top. So you can mix a movie like having a stem with 9.1 music and 9.1 dialogue and 9.1 ambience, and then eventually use objects only for some particular sounds like a car passing by, a helicopter, those kind of things. Besides Dolby Atmos, of course, there are many other formats like Auro Max or DTX-X and others. So the advantage of this is, okay, is this best space resolution that you could get, because it's almost like a vector kind of approach. It works for any layout, great. So what are the problems? Well, you need to distribute a lot of channels, and eventually for a movie this could not be an issue. But if you are doing things like streaming or broadcasting, to send 100 channels, that could be an issue. And also, you are limited to the number of objects that you can use. Once again, 128, it may seem a lot, but for instance, we have some of our clients using our application and have things like 10,000 sounds playing at the same time. And I'm crazy enough to have renders up to 1 million sounds, and of course you cannot have 1 million objects being rendered in real time on the playback. Also, some interesting curiosity. This movie from 1940s called Fantasia, that everyone knows with Mickey Mouse. At some point, Walt Disney thought that this movie that is essentially based on music should have a special sound system to people really get the most of the movie, so they have created something called the Fantasound system. That was a system that went from theaters to theaters, of course not in every single theater, but allows some people to get a better experience with the movie. And this is being considered the first movie to actually use surround sound. Also, in some versions of this Fantasound system, there was speakers in the ceiling, so it was also the first immersive audio kind of movie. And the interesting thing is that they made this by having a 4-track recorder, okay, 3 tracks for audio and 1 track for controlling. And essentially, this additional track would control where each one of those 3 audio channels should go. And at some point, it could go for the left channel. Later on, it could be to the ceiling, to the sides. So actually, this was also the first object-based movie. So people on the 40s, well, in front of their time. So object-based audio, you say, great, how can I use it? Well, the problem is that plugin architectures don't support yet object-based audio. I'm guessing that Soul maybe. Also, one problem is that digital audio workstations most of the times don't allow a plugin to control another plugin. So eventually you could say, okay, I'm not using object-based audio, but I could eventually try to control the Dolby Atmos spanner or something like that. So, but most plugins don't, most plugin architecture or most hosts don't actually allow you to do this. What you can eventually do is there is this new file format called ADM that was being pushed by BBC that support metadata for object-based audio. So eventually, could, if you want to explore more about object-based audio, this could be a good starting point. Okay, 2 already down the road. Let's talk about Ambisonics. But before actually talking about Ambisonics, I'm going to talk about a different format that could eventually help you understand better what is Ambisonics. Because a lot of people think that Ambisonics is like black magic, ooh, something kind of audio over there. So let's talk about mid-side. So middle side, it's a widely used stereo technique. Essentially what you do is you have a cardioid facing to the front of you, a figure of 8 pointing to the sides, which means that the cardioid will capture the frontal side of things, and then the figure of 8, since you have a null in the front, in the 0, it's on the back, it's 90 degrees. So essentially, the figure of 8 will not capture anything from the front, but only things from the side. So essentially, you get this mid that represents the mono component of sound, and then you get this side that represents the non-mono component of sound. But besides being used as a mic technique, this can also be used as a matrix, which means that you can convert a left-right audio stream into a mid-side, like mono and non-mono component, and you can convert back into left-right. For instance, mastering engineers use this a lot when they want to do something. Imagine that you want to make some kind of equalization to the voice, but the mix is done, you already have the final stereo. Instead of applying the equalization to everything, what you do is you convert to left into a mid-side. You apply the equalization only on the mid, so essentially mainly on the things and center, and then what you do is convert back to the left-right. So essentially, you have left-right convert into something else that you can easily convert back to the left-right. And how can you convert this? Okay, quite easy. If you have left and right and you mix sum them together, you get this mono component, of course. Okay, if you do left minus right, anything that is common to both channels will disappear. You get side. Sometimes people even do some kind of stereo processors that essentially what they do is simply convert mid-side, change the gain of the mid of the sides, and then back to the left-right. So to convert back to left, if you sum mid and side, so mid is left plus right, side is left minus right, so you have the left channel. If you do the same thing for the right, you get the mid minus side, you get the right channel. Okay. Let's now talk about Ambisonics and understand why this could help. So Ambisonics was created on the 70s, and the idea was, okay, let's try to create a format that is independent of the layout configuration that I'm using it. So when you talk about Ambisonics, and now let's talk about first-order Ambisonics B format, that is the widely the flavor of Ambisonics that everyone uses. So essentially, we have 4 channels of audio. The first channel, it's the Omni component. It's exactly the same thing as placing an Omni microphone on the room and capturing sound from it, okay? Then you have 3 channels, okay, that will represent exactly as having figure of 8 with different axes. So imagine that you place a figure of 8 left, right, another figure of 8 front, back, and another figure of 8 top, down, okay? And by doing this, these are the 4 channels that you get from Ambisonics, okay? Be careful because although this represents audio, you cannot feed this directly to the speakers the same way that you cannot feed the mid side directly to the speakers. Essentially, you have to have a matrix to decompose this to the speakers, okay? So, of course, you can do Ambisonics recording with an Omni and 3 figure of 8, but the problem with that is that to make sure that you get the timing perfectly, phases and so on, they decided, okay, it's much easier if we can use this kind of microphone like you see on this picture with 4 capsules together in this tetrahedral kind of approach. So essentially you get the left front up, the right front down, left back down, right back up. So by having these microphones, you are able to capture a good representation of your 3D sound field. But be careful because this is what is called a format. So essentially you have these 4 channels, but then you need to convert these for those W, X, Y, Z format. So essentially it's a format and need to convert this to the other, but that is also something quite easy to do. Simply mix these together, invert some phases, and you get those B formats kind of Ambisonics. So Ambisonics, great, 4 channels. You can represent an accurate 3D representation only with 4 channels, right? Yeah, not really, okay? So what happens is that Ambisonics, with first-order Ambisonics, these 4 channels, they give you a good representation of your 3D space, but it's not a very accurate one. For instance, if you have a sound coming from there, if you change that to Ambisonics, what you're going to listen is a sound coming from there, almost like some kind of defocus, spatial defocus happening from here. So what can you do to increase the accuracy of this 3D space? Essentially, you do something called high-order Ambisonics, which means that instead of having only 4 channels, you increase the number of channels to get more space resolution. And in here, what you see, it's the Omni component. Then you have these 3 additional format, 3 additional audio channels for the first-order Ambisonics, okay? The figure of 8 that you see. And now imagine that you want more accurate representation. You go for second-order Ambisonics. And now instead of 4, you have 9 channels of audio, okay? And if you want even more accurate, you can go to third-order Ambisonics, now with 16 channels of audio. And you can continue even creating something. For instance, 6th-order Ambisonics supports, needs 49 channels of audio, and it's laser blade almost. So you get additional, by having additional sound sources, additional audio channels, you get more accurate by having second-order, third-order Ambisonics. When you talk about Ambisonics, be careful because there are so many different flavors of Ambisonics, and you need to make sure that you are working on the exact flavor of Ambisonics. First, we have seen you get first order ambisonics, second order ambisonics, third order ambisonics. The good news is that this is easy. If you have 4 channels, it's first order. If you have 9 channels, second order, and so on, okay? So that's easy. The second is, okay, is this B format or A format, okay? Because someone could be recording something with the Ambisonics microphone, okay, is sending this in A format, and you need to make sure that is A format or B format, because A format and B formats are different things, okay? So A format represents these signals coming from this tetrahedral kind of microphone. B format represents something different, the omni and the 3 axes. Next, there is something called the channel order, because what is the second channel? Is this the right, left, right, top, down, front, back, okay? Because there is 2 different ways of ordering channels in Ambisonics. There was the old way called FUMA and the new ACN that everyone is using now, but be careful because you need to make sure that is the right channel order. Finally, there is normalization, and what is normalization? Depending on the flavor of Ambisonics that you are using, each channel going to have different gains, okay? Usually, today, most people use this SN3D. The advantage of SN3D is that you are always making sure that the first channel is the one with the highest amplitude, okay? So if the first channel is not clipping, you don't need to worry with anything else, okay? With other normalizations like N3D and so on, what happens is that the first channel, the omni, could be not clipping, but if a sound starts to move, starts to clipping on the other channel. So be careful, because normalization have different gains. Also, one interesting application for Ambisonics is VR, because with Ambisonics you can easily do rotations. If you imagine that you want to rotate the sound like this, or rotate the sound like this, or even rotate the sound like this, you can easily do that with a simple matrix, okay? So this is perfect for VR. Why? Because you have a way for representing 3D sound, you have a low channel count, and also you easily apply rotations. And VR are mainly about rotations. You have the sound, and then you do like this, and you have to rotate, rotate, rotate. So essentially, you can easily do all of this in audio using matrix. Once again, you are a developer. You say, oh, great, let's start supporting some Ambisonics and do something like an Ambisonics spanner. Well, what happens is that each channel is going to have a formula based on azimuth and elevation. For instance, this is an example of a formula, okay? For N3D ACN1, it's square of 3 multiplied by cosine of elevation multiplied by the sine of azimuth, okay? So you get several formulas for all your channels, okay? Don't forget about normalization. And I have good news and bad news. The good news is that there is this site with a lot of information about Ambisonics, that is this ambisonics.ch. The bad news is that the site is down for several months now, okay? The more or less good news is that there is this site called Web Archive, where actually you can visit sites as they were several months or even years ago. So eventually, if you try to access through Web Archive, you can actually go there and get all of this information about Ambisonics. Now imagine that you don't want to pan, but you want to simply apply rotations to azimuth on your next plugin. Essentially what you do is there are 3 rotations, yaw, pitch, and elevation, okay? So all you have to do is apply a matrix to the audio, and for instance, if you want for first order and second order Ambisonics, you have the matrix in this page. If you want for third order or higher, you need to do some additional work. Now let's focus about binaural. So binaural, the idea of binaural is to represent a 3D sound but using only headphones. So the question is, okay, can we simulate 3D sound with headphones? And the answer is, okay, if you can listen to with 2 ears, we can also reproduce that with headphones. So how can I implement this? So what do we know about sound directions? Well, if a sound is coming from there, what happens is that the amplitude is going to be higher in this here than this one. It's going to arrive first here than this. Depending on the position, it's going to have some reflections like from the shoulders and this highly detailed design accessory that everyone has called the ears. Okay, so in different sides of the pinna. So essentially what we do have is amplitude, time, delays, filters. So all of this can be represented with an impulse response. So if I want to represent the sound coming from this direction, only thing that I need is a pair of impulse response. An impulse response for the right ear and an impulse response for the left ear, okay? So essentially what we do is we have this impulse response for each position and for each ear, and this is called head-related transfer functions or head-related impulse responses. They are the same thing. In here we are talking about frequency domain, in here we are talking about time domain, but essentially it's the same thing. So how can I create a data set? Well, if you want to create a data set, you simply use this dummy head like you see on the image, or eventually you use very small microphones positioned on the ears of someone, and then you start capture the impulse responses for different positions around you, and you get all these impulse responses. The good news is that you don't need to do any of this. There are already several data sets freely available that you can use if you want to apply binaural to your next audio software. So, as a developer, what you're going to do, okay, imagine that I have this mono signal that I want to be perceived as a 3D position, for instance, coming over there. So what I do is, okay, I'm going to look at my data set. I'm going to see what is the position from my data set is closer to that position. If I want, I can even interpolate between more than one there. And by doing this, it's going to give me the impulse response for the left ear and for the right ear. And now, only thing that you need to do is to apply this convolution to the signal with this impulse response. This goes to the left ear, the same thing with the right impulse response for the right ear. And to those that don't know what is a convolution, it's 2 cycles very easily. Simply do a quick Wikipedia search and you're going to find out. Also, this binaural approach, it's the main approach regarding 3D sound for headphones. So video games, VR, everyone is using binaural to support this 3D with using headphones. So great, 3D sound over headphones for everyone, right? Yeah, not really. Okay, so what is the problem now? Well, the problem is that each person has different heads, different ears, okay, which means that you could have a fantastic data set for binaural, and that data set could work great with 70% of people, but will going to work not as good with 30% of people. For instance, with me, probably I have strange ears or something. When I listen to something in binaural, things from the front will always sound coming from here. So essentially, this is going to work for a lot of people, not for the other people, because people that have different head sizes here, different ears, whatever, it's not to be exactly perfect, okay? So a data set may work great for some, not for others. Which means that most times what people try to do is, okay, let's use the baseline that is better for the maximum amount of people, okay? For instance, 1 year or 2 years ago, YouTube have changed the data set they were using for binaural render because they found out there was a new one that was slightly better for more people, okay? So it's a data set that works best for most people. Eventually, if you really want people to have a very good experience, you need to create a way some customized things, or eventually allow a user to select which is the best data set. Imagine that you have several data sets and the user could pick up one of them. Don't ask me how, but it's an idea. Eventually there is, if you are very rich and interested in audio, you can make your own data set, okay, and some other reason. So be careful, because with binaural, it's not going to work for everyone the same way. In conclusion, so we have these 4 different approaches, each one with advantages and disadvantages regarding 3D audio. Of course, there isn't one single approach that's going to be best for every single situation, so you need to take that into consideration. And I hope that I could eventually help you get a slightly better understanding regarding 3D audio and the several flavors of 3D audio. And that's it. Thank you.
Excellent stuff. Thanks very much, Nuno. We have time for questions. Who would like to start? Freddy?
Thank you very much. Very interesting talk. I have a question. I'm not sure it will be interesting for everyone, so if so, please let me, I will ask afterwards. But what was always bothering me, you mentioned in the beginning this panning law, which is kind of linear with -6 decibel drop. And I know like this explanation for me works perfectly for crossfading. And I also know it works in practice for panning, but I always thought that like in panning you would basically apply gains to the same signal, which means the signal is 100% correlated with itself. And then I would think that not the powers will add, but the amplitudes will add. And actually you need linear crossfading. I know it's not like this in reality, but it was always bothering me, like why?
There are several things that need to be taken into consideration regarding panning. One of them is all of these are going to work differently if you are an anechoic chamber, if you are a place with more revolution, more reverb, less reverb. Okay, so there is something that slightly changed. And for instance, at some point, Disney made some tests and found out that the best solution was one. And then BBC, more or less at the same time, made different tests with a different environment, and they found out that the different panning law would be different. So essentially, there is slight nuances here. What happens most of the time is if you do this in a linear way, the power, the signal that comes to your ears depends on the powers of the speaker. So essentially, the power, it's voltage versus intensity, okay? That is the same as voltage over resistance or independent intensity. So the idea is by having the same power law, you get a more sense of more kind, because what you want is when you pan, you don't want sounds to start going low and upper. So that is by having sure that you try to continue to have the same amount of power coming out of the system for the user will be a more linear kind of effect. Nevertheless, it's be careful because depending on the acoustic situations of the room, that could actually not happen. So eventually, in some situations, you could have better results with different panning laws. Like, for instance, I think it's SSL mixers that use minus 4.5 dBs as a curve. So essentially, it depends on the situation. Thank you.
Okay, there was a hand up at the back. So yeah, you were talking about the okay, so there's the difference between the format and the order. So bearing in mind that distinction, so obviously the order is, you know, the law goes the higher the order ascends, the greater your spatial image. But could I in theory implement a higher order, encode something into a higher order system and then decode it to a format which is supported for binaural reproduction, or, you know,
yeah,
whatever. Yeah,
and actually that happens a lot. Every single VR client that you have today, what they usually do is you create all your audio materials in Ambisonics. So essentially imagine that you have a 360-degree video. So essentially you say, okay, I have a car passing there, someone talking over here, a river flowing over here, and essentially you create everything as Ambisonics, okay? And what happens is that when you are with your headset and you are moving your head, imagine that you do something like this. What they do is they use the Ambisonics, they rotate the Ambisonics considering the rotation of your headset, and then what they do is they convert from Ambisonics to binaural. Okay, so essentially it's the same thing. It's also a matrix, okay, that you apply to all the channels, and by doing this, you get your final Ambisonics. For instance, a few months ago, Google have released what is the matrix that they are using on YouTube to convert from Ambisonics to binaural. So for those that want to create something to make sure that it's exactly the same behavior as it's going to be on YouTube, you can apply the same matrix to convert into Ambisonics, from Ambisonics to binaural, applying that matrix.
Oh, thanks. Thanks again for the talk. So you mentioned that for Atmos, it's difficult for plugins to kind of dig in and get their hands dirty. And I was wondering if that's also true for Ambisonics, or in general, what tools people use to author Ambisonics materials.
No. In Ambisonics, it's easier now because at some point it was mainly Reaper that supported Ambisonics because it's more flexible in terms of buses. And then we get Ambisonics support from additional workstations like Nuendo and Pro Tools. And Ambisonics, it's more easy to implement from the workstation point of view because it's still audio. You still go there, get the audio, apply something to there and change the audio. So it's still audio. The problem with object-based audio is that you slightly need to change things differently. Your bus, it's not going to be any longer only an audio bus. You also need to have some metadata. And now imagine that I have some kind of plugin that uses it's a delay. And what I want to do with the plugin is I have two objects. One of them is the original sound, but I also want to output a delay coming from a different position. So essentially, you get one object audio coming in, okay, one audio stream with metadata, and then you want to output two objects, or eventually three objects, because it's a multi-tap delay or whatever. So it's much harder for the digital audio workstations to implement that. They can implement that, but they need to change the core of everything, and it's going to be harder because, like I mentioned, Ambisonics is still audio, okay? You still get the audio, you mix everything, you move audio on to the next stage. Eventually, you can create some additional tools like convert that Ambisonics, for instance, to stereo, binaural, or 5.1 or whatever, okay? But essentially, the core, it's exactly the same. With object, you need to change things because you start to add on the buses metadata that were not created in that way.
Okay, question from that side of the room?
So you explained how to position a source in a 3D space using HRTF or Ambisonics. I was wondering, what's your favorite method of rendering the distance from a source?
So in terms of distance, what happens, for instance, I can tell you what we have done with sound particles, is that with distance, there are several things that affect distance. One of them, in terms of panning, most of the times you want more or less, okay, if you have a sound coming like 3 meters away, it's still 3 meters away. If they are coming farther away, it's still the same panning, okay? Also, another thing that you need to be taking into consideration is that with distance, you get different frequency equalization. That's one of the things that we want to add on the sound particles. We even have already released a plugin that does that, but now we need to implement that to make sure that you get the different frequency response. But what usually most people use in terms of binaural is to simply use a data set that, besides having this kind of positions, also have distance into consideration. So eventually, imagine the data set that I've made the distance, this position, and for instance, that position. Okay, and by having this, of course, everyone quickly understands that, especially things that are too close, for instance, something like this will be completely different than something like this. Okay, so actually there are a few data sets, not much, that also take into consideration the distance and then use this to do that. Also, besides data sets, there are some companies that are creating 3D engines and render engines that also model this kind of behavior to make sure that depending on the distance you get different kind of behavior. Besides that, there is also something that you can do and that affects reverb, because the reverb that you get could be slightly different. But most of the times what you do is to have different data sets, especially for very near kind of sound. If there is like 3 meters versus 10 meters, it's not going to be a huge difference, but something close to the person, it's going to be completely different. And for that, the best approach would be to get a data set specifically for different distances, not only azimuths and elevations.
Got time for one more. Oh, we've got 3. Okay, see how quick they go.
In any of these architectures, is there also provision for indicating motion by some kind of Doppler effect?
Yeah, actually what we do with sound particles, what we have done, it was not adding support for Doppler, but actually writing code if you want to disable Doppler. Because what we do is when we have a sound coming like 100 meters away, we already apply the propagation delay to the sound. And by doing this, what happens is that as the sound moves, you get the Doppler. And actually, one of the things that people really loved about our product was the Doppler. And I recall at some point David Farmer, the guy from Lord of the Rings, told me, okay, this is the best Doppler by software that I've used. And I said, really? Because I thought, okay, it's Doppler. It should be already a lot of Dopplers over there. And essentially, I'm going to tell you the secret sauce, but what we have done is we are simply modeling this per sample. So essentially you are applying this per sample, so you get a very accurate kind of Doppler. What we have done was there is a checkbox if you want to disable Doppler, but that we have to write code to overcome that and say, okay, let's consider only the initial delay of the sound and then use the stream considering that same amount of delay. So we have to add code to disable Doppler.
Okay, let's squeeze one more quick one in. So, anyone? You had your hand up first.
Is it possible to calibrate the binaural experience individually?
There are people trying to do that. For instance, imagine that you get the data set, but imagine that the person is have a head that is slightly different, so eventually you make some kind of adjustment. For instance, imagine that you place something that should come like 45 degrees to the side, and you ask the user, okay, this sound, where do you think is coming from? And you say, if you say that it's slightly to a different position, you then use that information to slightly calibrate things. So yes, it's possible. There are a few 3D engines using that information, but it's not that easy.
Okay, we're out of time, but let's say thanks once more to Nuno Fonseca.
Thank you.